The project title is Diesel Maximization by using vegetable oil, which is Jatropha oil in Petroleum Refinery. This project was done by Mr. S. Bhupati and H. Rafi Ahmed of Beltech High-Tech, Dr. Angujadan and Dr. Sakuntala Engineering College. This project is being done in Chennai Petroleum Corporation Limited. The abstract of the process is the energy resources that we like petrol and diesel are depleting nowadays. So to overcome this problem, we have to use natural energy sources like vegetable oil and animal fats. So we are using Jatropha oil to blend with raw diesel to produce high diesel at high purity without any impurities. Company profile. The Chennai Petroleum Corporation is Indian state-owned oil and gas corporation headquarters in Chennai. It was formed as a joint venture in 1965 with GOA, Amarco and NIOC. It has two refineries located at Manali and Nagapatnam, overall capacity of 11.5 MMTPA. Introduction to the project. Jatropha carcass is a piece of flowering and fruit-bearing plant in genus Jatropha. Its seeds contain 27 to 40% of oil. So this oil is being blended with diesel in diesel hydrotreating units of Petroleum Refinery. The objective of the process is to develop a new alternate version for biodiesel by using method of blending technology, also to produce high efficient diesel by blending diesel with vegetable oil with low sulfur content, lower density and high cetane number, also to design a reactor column for our desired feed rates. Moving on to the process, the raw material used are raw diesel from ADU outlet, vegetable oil from the storage tank and hydrogen gas. The process parameters are temperature is equal to 350 degrees Celsius and pressure is equal to 65 kgf per centimeter square. Process description. The linear state and reserve and from the ADU is blended with 10% of Jatropha oil and pumped by a centrifugal pump. Then is sent to a small storage vessel with diesel is free for water content. After passing to the storage vessel, vegetable oil is being added to the reserve for blending. Then by using pump, it is transported to the furnace for better conversion. Hydrogen is added to the diesel oil mixture from the hydrogen is forming unit so that the impurities react with impurities present diesel will react with hydrogen and finally the diesel is free from impurities. This is the overall process flow sheet for our project. It has contained reactor, furnace, separator, which are maintained at a constant temperature and pressure. Material balance for the reactor. The material balance for the reactor is 90% of diesel function from the atmosphere is given, 10% of Jatropha oil is used as feed for the reactor. There are three major reactions that occur in the reactor. That is, reaction 1 is benzothiophene reacts with hydrogen and forms ethylbenzene, dibenzothiophene reacts with hydrogen and forms biphenyl, and quinine which reacts with hydrogen and forms nonane. These are the three impurities that comes out from the reactor outlet. Feed composition is given by this CPCl. This is a composition of diesel which contains paraffin, naphthalene, aromatic, dibenzothiophene, benzothiophene, and quinine. Expected conversion for our project is 85% reaction temperature and basis we are taking 100% kilomole hour of feed, and material balance is rate of mass in for rate of mass out. Also we calculate the total H2 chem for 100% conversion is equal to 40.22 kilomole per hour. So now we have to determine the periodic item for required 80% conversion. For 80% conversion, we calculated this. We got 34.19 kilomole per hour, and also excess hydrogen is being supplied so that the reaction may occur fast. So total hydrogen is sent to 68.38 kilomole per hour. Well, this slide shows the overall material balance at the inlet of the reactor. That is, mixed feed is 100, H2 by 68.38, and total moles entering is 168.38 kilomole per hour. This slide shows the molar composition of feed to the reactor with the components, the molar flow rate, the molecular weight, and the mass flow rate. The total mass flow rate entering to the reactor is 18,109.65 kg per hour. And this slide shows the molar flow rate at the outlet of the reactor along with the components, molar flow rate, molecular weight, the mole percentage, and also with the mass flow rate. So at the end of the outlet of the reactor, the mass flow rate also is 18,109.6 kg per hour. This is the overall material balance for the reactor. Inlet is equal to outlet. Thus, the material balance is satisfied for the reactor. Now, moving on to the energy balance for the adiabatic reaction. The energy balance for the adiabatic for reaction 1, the heat of the reaction is being calculated, and for reaction 2, the standard heat of reaction for is being calculated. Moving to the reaction 3 also, the standard heat of formation is being calculated, and total enthalpy of the reaction is minus 1196.236 10 to the power kilojoule per hour, and total enthalpy in is also being calculated, and total enthalpy out is going to be calculated. Thus, the overall energy balance is total enthalpy in is equal to total enthalpy out, and we calculate total enthalpy in, and we know the outlet temperature, so we are finding the reactor outlet temperature to be 358 degrees Celsius. If we substitute the temperature, inlet will be equal to outlet. Now going to the design of multi-phase adiabatic fixed bed reactor. The design equation of flexible reactor is being used, and also the expansion pattern for the reaction 1, reaction 2, and reaction 3 is being calculated. From that, overall average expansion factor is also being calculated. Determination of volumetric flow rate. The volumetric flow rate must be calculated for the design of the reactor. We know the mass flow rate. From we are calculating the average density by calculating the mole fraction also. Determination of average density. Density of the feed and density of the is being connected, and we took the average density, and by using this average density, we used to find the volumetric flow rate of the reactor, and also we find the initial concentration of the feed also. In this slide, we are calculating the volume of the reactor by using that equation and substituting the concentration values and the space-time values on the plug flow reactor equation, and we get the volume of the reactor at 53.95 meter cube. We are finding the diameter of the reactor and height of the reactor, and we are using, since we are using new catalyst, we must know the volume of the reactor, volume of the catalyst in the occupied in the reactor. So we are using the new catalyst or nickel monomer catalyst, and we calculate the volume of the catalyst. On this slide is where we calculate the total volume of the catalyst present in the reactor and also the void volume, and we are moving into the pressure drop in the reactor by using the Ergen equation. We calculated the porosity, average viscosity, average density, and also the superficial mass velocity by all using this equation. And the specificity of the catalyst is 1, and the diameter is converted into meter. And we are substituting all the values in the Ergen equation so that we get the overall pressure drop, and pressure drop in each bed is being calculated, and also the total pressure drop is being calculated and converted into kg force per centimeter square. On this slide, we are calculating the mean reference time distribution of PFR, liquid hour space velocity, and also the calculation of field. In the calculation of field, we expected the conversion 85%. Also, it has been proved.